Hello, and welcome to my Lab 5 video report where I will be modeling projectile motion in two dimensions using two equations. So first, I will observe and model the motion of a ball undergoing projectile motion. Then I'll use Newton's second law and the basic kinematic equations from high school and Calculus 1 to model the motion of the system, which is the ball. I will compare the two models' results and discuss the pros and cons of the models. Newton's second law did a better job predicting the motion, but the kinematics equations were just much easier to use in motion prediction. Why did I choose to explore this adventure? The kinematic equations learned in Calculus 1 or AP Physics B or high school honors physics have never been spoken about in this course. This poses the question on whether those equations were valid equations or were just bad approximations of motion. Therefore, using both Newton's second law and the kinematic equations, the motion of a ball rolling off of a table will be modeled and discussed. This is the motion of the ball I've observed in tracker. Newton's second law is used to predict the position of the system after a short time interval. The system chosen here is the ball, and everything else, such as the earth and the hand, are the surroundings. And Newton's second law says that the total sum of all the forces is equal to the change in momentum or the change in time, which is the same thing as the mass times the change in velocity over the change in time. The position can therefore be calculated using this equation right here, where we use the approximation that V average is the same as V final. The two important definitions of motion, the definition of acceleration and the definition of velocity, can be used. The two important definitions of motion, the definition of acceleration and the definition of average velocity, can be used to predict the motion of the system if the time t is known, which it is known here. Here we make the substitution delta t equals to t, since we set t initial to be 0 and t final to be some arbitrary value t. The proof for the kinematic position equation can be shown here. Taking the definition of acceleration, we rearrange it to find the final velocity. Then taking the position formula we have used in class, we plug in the final velocity in here to get this equation. After we do some simplifying of terms, we get the final position kinematics equation that we have learned in high school. An alternative proof is to take an acceleration value that is some constant and integrate it so that we get the velocity, which is equal to the acceleration times time plus the initial velocity. Then we take the velocity and we integrate it again to get the position, which results in the exact same equation as we have found here. So observations we can make about our system before we make any calculations is that initially the ball is just translating along the x-axis. So the acceleration along the x-axis is 0 if we neglect air resistance. The velocity of the ball before falling off the table can be treated as approximately constant and can be computed by taking two position points before the ball falls off of the table. The only force acting on the system during free fall is gravity if air resistance or drag is neglected. The x direction experiences no net force, but the y direction does due to gravity. So from intuition, the x component of the velocity should remain mostly constant throughout the motion. Using our two equations, Newton's second law and the position equation, as well as the kinematics equation of position, the motion of the ball will be obtained from VPython. For the sake of time, the program will not be ran here. If you want to see the code, you can pause and look at the code here. This is the result from using Newton's second law to predict the motion. The motion along the x-axis seems pretty constant, except the experimental data has a few jittery points here and there. Overall, though, it matches pretty linearly, just like the model predicts. The y direction is not so exact in terms of modeling the motion. The experimental data seems like the ball's motion is moving down sharply and then flattens out near the end, whereas the model predicts that it's a completely perfect parabolic shape. Using the kinematics equation for the x data, we see that it predicts that the motion along the x direction is linear, or that there's constant velocity, just like we as assumed, and just like Newton's second law is assumed. The y data is also very much the same, where it predicts that it's a parabolic shape, except again, the experimental data dips down more and flattens out near the end down here. You can see that between the kinematics equation and Newton's second law, they're both more or less predict a parabolic shape, just like the experimental data shows. So two sources of error in this experiment are drag and plotting error for these reasons listed here. And the differences between the two models is that they can be used depending on how much data is available. Newton's second law is very precise if you have small time steps, but it requires knowing the mass and all the interactions in the system. The kinematics equation is very useful because if you know some arbitrary time t and the initial velocity and the acceleration, you can find the position and the velocity at any time t. This concludes my lab report. Thanks for watching.